Okay, live streaming is being prepared. Okay, I think we can start today's session. So I would like to welcome everyone to our final event, the class final event with the title A Novel Software Architecture for Real-Time Smart Cities. We are very excited to welcome you to our final event today. This is a special occasion for us. It's not just our final event, it's also the last day of the project. So we're both happy and sad to see this project finishing, but we are mostly excited to welcome you all today and to let you know of what we've been working on for all these years. So welcome and enjoy the event. I am Nicoleta Chiapidou. I'm the dissemination leader of the class project based at the Barcelona Supercomputing Center, and I will be moderating the event today. And I would like to introduce you our speakers. Of course, we have Eduardo Quiñones from the Barcelona Supercomputing Center, who is the class coordinator. We also have Luca Ciantone from Comune di Modena, Mara Tonietti from Maserati, Ereth Haddad from IBM Research Haifa, Ruth Palmero from Atos, Roberto Caviccioli from Unimore, and Eli Garzacli from Barcelona Supercomputing Center. They're all class partners, so we have a diverse panel who will explain you all about the class software architecture and use case. I'll go through the agenda very quickly. So after this very short welcome, Eduardo will give an overview of the class project. Then we have a very exciting presentation about the smart city and connected cars use case with a live demo in the smart urban area of the Modena city. We will then have a short coffee break and we will continue with a bunch of presentations on the class data analytics platform, cloud computing, edge computing, the software architecture, and we will finish with the Q&A slot and the concluding remarks again from Eduardo Quiñones, our coordinator. So just before we start with the actual presentations, I would like to give you some housekeeping rules, let's say. So the session is being recorded at the moment, and the recording will be posted on our website and social media right after the event finishes. There will be time for questions after each presentation, so we will welcome all your questions and comments, but there will also be general Q&A slot at the very end of this session. You can ask your questions using the Q&A function on the Zoom window, so that would be very helpful for us to collect all of your questions there. You can also use the chat if you want, and if you would like to speak out loud, you can click on raise hand and I will unmute you. Basically, this could happen during the larger Q&A slot we have at the end of the session. But if you do that, just bear in mind that the session is being recorded. And if you have any questions throughout the event, just don't hesitate to chat with the panelists or send us an email at class-project@bsc.s. And that's from my side. I will stop sharing my screen now, and I think we can go ahead with Edu's presentation. Edu, I give the floor to you to give us an overview of the class project.
Thank you very much, Nicoleta. Thank you, everyone, to join this final class examination event. It is a great pleasure to be here in Modena. In fact, this is the first trip myself is doing in the last year. So for me, and as well as for other members of the team, it is very special to be here in Modena, finally, in this final examination event. Okay, so in my presentation, I'm going to provide an overview of the class project, focusing mainly on the key innovation that the class project is providing. That is a software architecture for the development, deployment, and execution of complex data analytics workflows. Before, let me start with just providing a very quick overview about what's class. So class is an Edge 2020 project. The name class stands for Edge and Cloud Computation, and a highly distributed software architecture for big data analytics. It has been a 42-month project. It was extended because of COVID, and the overall budget has been €4 million. So class is about how, from the data collected by the different sensors in the city, we can generate knowledge, valuable knowledge that then the city can use. So for example, we can have an image of a camera, and then from this image, we can, for example, determine the different objects, determine the trajectories, and then, for example, detect potential collisions before it happened. Or we can also, based on the dynamics properties of the different objects, we can compute in real time a map of the estimation of the level of pollution in a given area of the city. And to do this, what we need to do is to define a data analytics workflow in which the data is processed by different methods until providing the knowledge we are interested in. For example, in this case, in order to detect potential collisions, we would need to detect objects, track them, predict the trajectory of all them, and then identify whether there is a collision or not. And if we want to determine the level of pollution, we need to run simulation models based on the dynamics of the different detected objects. We can determine what is the level of pollution in a given time. Doing this for a single image, it's quite simple. But when we are focused in a smart city, there are a set of challenges that makes this process more difficult. Why is that? Because first thing, we don't have a single source of data. We have many different sources of data. So data sources are geographically distributed. And so data analytics requirements are also geographically distributed. Moreover, some of the functionalities smart cities wants to implement requires real-time requirements to fulfill real-time requirements. This means that the end-to-end response time of the workflow needs to be in a given time budget in order to guarantee the correct operation of the functionality. Okay, and so providing this in a distributed environment is very, very complex. So in this example, for example, we have 4 different data sources. Each of those is going to be computed, is going to process a given workflow. In this case, what we need? We need to have a distributed environment combining both edge computing and cloud computing. At the edge computing level, we are going to have very limited computation capabilities. But the response time is going to be very fast because we are not suffering in any communication delay. On the other side, on the cloud computing side, we are having high computation capabilities, but suffering due to the communication. So in order to really take benefit of this, what we call the compute continuum, we need to efficiently coordinate the edge and cloud resources such that the workflows that are executed provides the result in the time needed, in the time required. And this is exactly the vision of Class. That is, if we are able to distribute the complex data analytics workflows across the compute continuum, we will significantly increase the capabilities of data analytics. And the key element here is to allow us to integrate both responsive data in motion analysis as well as data at rest analytics into single complex workflow. One key element is the use of not only cloud resources, but also advanced parallel and energy efficient edge computing platforms. So we can provide at the edge level the required computing capabilities in order to implement the data in motion analytics. And of course, all this needs to be given in real time. And if there is an important word that the Class project has been pursuing is the word productivity. Class is about enhancing the software development productivity of complex data analytics workflows from 3 different angles. From a programmability angle, meaning we facilitate the developer to describe the workflow. From a portability and scalability angle, meaning this workflow is developed completely independent of the underlying platform, meaning that if the platform changes, the workflow will still execute. And of course, we want performance. We want to execute our workflows as fast as possible, providing real-time guarantees. And how Class has implemented this vision? This vision has been implemented by developing what we call the Class software architecture that integrates technologies from different computing domains. And all this has been integrated into a single development framework. So we have on one side a powerful API that allows us to develop, to describe, to include the data analytics methods into a workflow based on both task-based parallel programming models and map-reduced programming model. We have also provided advanced orchestration mechanisms with taking time predictability into account that allow us to deploy and schedule this workflow across the compute continuum. We have also provided quality of service serverless and container as a service cloud technology in order to extend this concept of real time at the cloud level. And of course, we are using the most advanced edge processor architectures in order to provide computing muscle to the edge layer as well, so we can provide this at real-time response. So here you can see a picture of the different technologies we have integrated into the software architecture that along this presentation we are going to present. And then this project has also a use case, a very challenging but exciting use case. So we have used our Class software architecture in order to develop advanced urban mobility functionalities and deploy them into the Modena Automotive Smart area in the city of Modena. Massa is a Living Lab urban area that includes IoT connectivity and a compute continuum infrastructure in order to execute our workflows. And we have also 2 connected cars equipped with sensors, cameras, and either in order to understand the surroundings and also communication with the cloud. And with this infrastructure, what we have done is we have developed 2 use cases that we really hope we will be able to show you, that shows how the information that is collected from the city and the information is collected from the vehicle. We can provide an advanced driving assistance systems based on collision detection, and also we can compute the level of pollution in a given area in real time. And just to conclude my talk, let me just provide a snapshot, okay, of what are you going to see today. So, as I said before, class is about facilitating the deployment, the development, deployment, and execution of advanced workflows. So, in this video here, and this video you are going to see it along the different presentations. We want to implement, we want to detect when 2 cars can potentially collide. In order to implement this, you need a set of methods, data analytics methods that you need to combine among them. From the data sources, you need to combine among them in order to provide the valuable knowledge that you need. In this case, determining a collision. What class has done is, first, it facilitates the development by describing your functionality as a workflow in which the data flows across them and generates the knowledge needed. We are also deploying this, so determining what is the best computing resource in which the different data analytics methods must execute in order to minimize the execution time, minimize communication latency, and provide a real-time requirements. And finally, we execute using the different technologies included in the class software architecture. All this is going to be explained across along the different presentations you are going to see today. So thank you very much. And if there is any question.
Thank you, Edu, for this overview. It was a great way to start our event today. So let's see if there are any questions at the moment. As I said in my short introduction, people can use the chat if they like. They can use the Q&A function as well. It's the option you can see at the bottom of your Zoom window. So let's see if anyone has any initial question. If not, I think we can continue with the next presentation. I'm just going to share my screen very quickly to show the agenda. Just a reminder of the agenda. So we will go ahead, as Edu mentioned, with the smart city use case. Now we have a presentation by Luca Ciantore, Mara Tognetti, and Eduardo Quiñones. It's a very exciting part of our event today, and we're gonna show a live demo as well. So I'll give the floor to our 3 speakers now, who will have their short presentations, and then, as I said, we will attempt a live demo with the Maserati cars in the smart urban area of the Modena city. So let's start with Luca. I think Luca is ready.
Yes, I'm ready.
The floor is yours, Luca.
Okay, I'm ready. Good morning. Thank you very much to everyone. I'm Luca Ciantore, the Chief Information Officer of the City of Modena, and also the Smart City Manager. It's a great pleasure for us to host the Smart City use case of the class project. a brief introduction to the city of Modena. The city of Modena is a small city that join culture, tradition, in general, good life, beautiful car, because we have a lot of beautiful cars, and also innovation. There is a very important document for us, our digital plan, approved by the City Council in 2020. In this digital plan, we define the pillar of the digital innovation in the city. And as you can see, we have 3 pillars. The first one about digital infrastructure. The second one about online services for citizens. And the third one is about strategic projects. CLASS for us is a very, very important project. It is a strategic project. In general, European projects are very important, in particular in the innovation field. We have also another very, very important project for us, that is the MASA project, the Modena Automotive Smart Area project. And CLASS and MASA join. We have a link, a strict link between these 2 projects. And then I will describe why. MASA is our program of development in the field of research for automotive and for new devices, for a new mobility, for a safer mobility, a green mobility. And in the MASA project, we have, of course, technical skill about artificial intelligence, cybersecurity, research group, of course, artificial intelligence, cybersecurity, real-time research on real-time, because we need real-time response to develop this kind of devices, but also skill in law field and in economics. So a multidisciplinary approach. And MASA project join CLASS, because the MASA project is a sort of living lab. This living lab is close to the center of the city. You can see the map. Is a sort of urban racetrack, a ring, with some very important point for our research, for a roundabout, a bridge, and some other interesting point, because they are near to an hospital and the new data center of the city. This living lab has fundamentally three elements, 3 assets: a sensing infrastructure, a communication infrastructure, and a computing infrastructure. All these assets are at disposal of the CLASS project. In detail, the communication infrastructure. We have all the area. In all the area, there is a network. Many network, a wired network in fiber optical, the red segment in the map, and some wireless network. In particular, we have a 5G antenna, a 4.5, a 4G antenna, private 4G infrastructure. This antenna is on the highest building in the area, and also a LoRa antenna for devices that doesn't need real-time approach. Then we have a sensing infrastructure. In the map, you can see where are the elements. Fundamentally, we have camera, traditional camera, that use the edge node named fog node to extract information and value from images and give this data, this information to the class software architecture. Then we have also smart camera. Smart camera are camera with a GPU on board, and they can elaborate, they can compute information on board of this device. And then we have also pollution sensor, parking sensor, and so on. The computing infrastructure, finally, we have also a new data center. In the region, in the Emilia-Romagna region, now we have 4 public data centers. Modena is the last one. And inside this data center, we use a lot of computing resources. So we have a virtual infrastructure and a lot of virtual machine to create the city cloud. But also we have the edge node on the road to support a computation on the road. So we have computing resources at the edge node and also on the cloud. Finally, we have defined also in the project a data model, because of course when we manage images, we need to be very pay attention, strict attention to regulation, privacy regulation in general, to the GDPR. So we defined a policy. We collect only anonymous data, so not personal data. We have defined 3 levels of that data set. The first one is a disaggregated level. So we record for a short time the position of an object and the timestamp. But then we have two levels of aggregation. So after a day, we aggregate this record, and then we do another level of aggregation. This to be sure that we can have a full compliance with GDPR rules. In the last slide, last one, stop. Okay, in the last slide, you can see the data flow. So in our area, we have a city infrastructure with an edge level and a cloud level, but also we have car. So now I give the floor to Mara for her presentation. Also, car are sensor. So in class project, car can talk with the city. Okay. My presentation is finished. If someone has a question.
Thank you. Thanks very much, Luca. Thanks very much for this. So it was great to hear about the view of the city for the class project. And I think we can go ahead with Mara's presentation straight away. And if there are any questions, we can check them after the live demo. So as I said before, if there are any questions during the presentations, feel free to click on the Q&A and ask them there, or use the chat. But we will allow questions after this session, I think. So maybe we can continue with Mara's presentation. once she's ready. Mara is going to talk about the Maserati cars and how they're censored and how they're used in the project. So Mara, whenever you're ready, I give the floor to you.
Okay.
Okay.
So thank you very much, Nicoletta, for the introduction, and thank you for all the team to make this project possible. It was a pleasure for us to join this project. I'm Mara Tonietti. I'm representing Maserati inside this project, and so I would like to give you a brief overview regarding the connected cars and sensing components. Within the class project, Maserati has provided 3 connected vehicles to the project. The first one is a Maserati Quattroporte, that is a luxury sports sedan vehicle, and it was provided at the beginning of the project in January 2018. The second vehicle is a Maserati Levante, a mid-size luxury crossover SUV, and it was provided in September 2018. The last vehicle was provided last year in June 2020 and is another Maserati Quattroporte vehicle. Both Quattroporte vehicles are equipped with a software for a LiDAR on the vehicle roof, and all the 3 vehicles are equipped with a full package ADAS, so Advanced Driver Assistance System optional package. Regarding the sensing components, each vehicle includes a set of sensors device to give information regarding the position of the vehicle, the speed, and the typology of the object that surround the vehicle. In addition to this data, the vehicle will provide also information from the vehicle CAN network, and including also the acceleration, collision, and the emergency brake information. All these components integrated with the computing platform will allow the vehicle to have to perform 3 main tasks: have a complete perception of the surroundings, have information regarding the vehicle positioning compared to the one already given by the vehicle, and finally have information about the infrastructure through the V2E communication. The surrounding perception is made using 6 different high-performance cameras. 4 of these cameras have a field of view of 120 degrees, and 2 have a field of view of 60 degrees. The car also are equipped with 1 LiDAR to detect the object around the vehicle, and 3 radar already equipped in the car, and also parking sensors already equipped in the cars to have a perception about the surroundings. So for the vehicle positioning, inside this project, we use the GPS, and so we have information from the vehicle through the maps and the GPS. And finally, as mentioned before, we have information about the infrastructure, so the surroundings of the car, using a 4G antenna for the V2E communication. Finally, each vehicle includes a powerful high-performance computing platform. This allows to implement all the data from the radar, LiDAR, and cameras. And in particular, for the first prototype, we used the NVIDIA Drive Pix2 Autochauffeur. For the second vehicle, the AGX Xavier, and for the third vehicle, the AGX Pegasus. So we are using 3 different platforms to make this fusion between all these components and to have real-time information regarding the data from the surroundings and the vehicle. This is, as mentioned before, a brief overview about the cars and all the components that are equipped in the car. So I leave just time for question and answer if you have. Otherwise, thank you very much to everyone.
Thanks very much, Mara. Thanks for sharing the perspective of Maserati in the project. So I think we can have the live demo now, and then we can allow some time for questions right after. So we wrap up this slot nicely. So as I said, after Lucas and Mara's presentations, we're going to attend the live demo with our Maserati cars in the Massa, which is the smart city area in Modena, as Luca mentioned. And right after this live demo, we will allow time for questions. So let's try to go for the live demo. I'm going to spotlight the Maserati car that is currently in the Massa, and also the Massa area as well. So I think now it's all viewed nicely. Is that correct?
Yes, we can see it nicely.
Great. So I give again the floor to you, Edu, and
Thank you very much, Nicoletta.
The rest of the people, and we start with this slot.
Okay, so thank you. Now is probably the most challenging part of the presentation, since we are going to test with what we have been developed. So now Francesco is showing one of the cars that we have been experimenting with. There is also another car in other part. Francesco, you see that he's just running. So then you can see the other car that is exactly over there. Okay. And this is the other car that we have been experimenting with. And this car, you will see, it is a Quattroporte vehicle, and with cameras mounted and with either mounted on top of it as well. And with these two cars and the information collected from a camera, we will try to do a demo. I hope it will work as smoothly, and it has been working the last days, but with the demo, you never know. Okay, so then if you can make my presentation bigger so we can focus on my presentation only, and then we will go back. So Nicoletta, would you mind to spotlight only my presentation?
Sure.
Thank you. So then we can focus on my presentation. Thank you.
Okay, done, no problem.
Thank you very much. Okay, so the demo is going to occur into the Modena Automotive Smart Area. And we are going to consider for this demo 3 cameras spotting 3 different parts of the city. The cars are in camera number 1, okay? So at the end, all the analysis of the results, we are going to focus on the camera number 1, but the rest of the cameras, but we are also going to show you what is going on in the other cameras, although we are not going to see videos for a GDPR reasons. So as I said, okay, no, wait a second. Okay, yes. Okay, so the video you are going to see is precisely this one. Okay, the demo you are going to see is precisely this one. So we are going to have the 2 cars that are advancing. Okay, the camera, the cities from the cameras plus the sensors from the car are going to identify this surroundings, and hopefully are going to detect that a collision has occurred. sometimes it happens, sometimes it not, because, you know, the two cars needs to do it very smoothly, you know, in order to reproduce that collision is going to occur. And of course, we are going not to collide the two cars. Can we then move to the 3D visualizer? Okay, so what you are seeing here is the real time of what's going on in this area. Right now, what you see is the two cars. Okay, the Levante car with the lights. So Roberto, you perhaps can zoom in precisely, and then the Quattroporte. And then around the Quattroporte, you can see that there are things spotting around. This is the information that the Quattroporte takes. Then the information from the cameras from the city are not spotted. Okay, why is that? Because this is still not active. We will activate now. We will execute the workflow now. Okay, so then you can see, and then you will see how the different spots, I mean, how the different information collected from the city and from the vehicles are shown in this 3D demo. We are also going to spot different parts of the city. Marco, Roberto, can you show the other parts? This is the other part that you are not seeing anything because, as I said, cameras are not yet active, and this is the other part. Okay, so let's move back. This is one car. This is the other car with the information that is being collected. Okay, and let's go back to this place. Okay, good. So let's then start. So, and Nicoletta, before, can you please spotlight the two cameras?
Sure. Yes.
So then you can also see what's going on. One camera, this is the car, and this is the panoramic view. Okay, so
okay,
let's rock.
Beniamino, you can start. Eudal, start.
Okay, so you see
Guido, bye.
So you see the two cars are approaching. Now you are starting to see that there have been warnings across there. They may be potential situations of risk. They may not be. You see here that there is also things running in this camera, and in this camera as well. There are spotlights and things that the cameras from the city have been detected, and now the car is going back to the position. Okay, so what we are going to do now. If you can now, Nicoletta, no, can you just show again my presentation? Okay. Okay, so this is the live demo. Okay, so during this execution, we have been collecting all the logs. So then you will see what has actually occurred. Okay, and then what we are going to do now is, as I said, collecting all this data and producing the videos, new videos, in order you can see what has happened. But just to give you an idea of what you are going to see, okay? In my presentation, in the left part, this is what we are. These are our target. Okay. So Nicoletta, perhaps can you please spotlight my presentation again?
Okay, I'm doing it now.
Thank you very much.
Sure.
Okay. So the first presentation, this is what we call an idealistic execution. So we have this was a test we did in April, May. once we had the pandemic, allowed us to do the tests. And there we ran like many times these tests in order to reproduce a collision. Okay, so the two cars were approaching like very, very close in order to reproduce a collision. Okay, and this was the result, and this is what we are producing now. So you see the two cars are approaching. We are computing the trajectories, and you see that the black spotlight. This black spotlight is that determines the collision. Okay, so we have been computing the trajectories of the two vehicles. We have completely removed the rest of the information collected, so we focus only on our interest. This is our point of interest. Now trajectories are computed, and you see we are computing the trajectory. This is, of course, let's say the ideal scenario. Okay, but in reality, what is happening is that all these workflows, okay, are going to be deployed, are going to be executed across the compute continuum. And so there are interferences among them. There is delay among the different executions. And so what you see on your right part of the image is what we obtained with the exact same video, but this time executing only with one camera only. So no, with two cameras only. So you see that you're going to see that you see here there are, let me show it again. So in this area, we are going to see, here it is, okay, that we have been, that there has been potential collisions identified. This time you see that the run is not that smooth because we were reading from videos from the streaming of the cameras. We were reading from the car. We were fusing the two information. We were computing trajectories of all the area. We were computing collisions of all the area, and this is delaying, okay, the execution. So then what I suggest now, and Nicoletta, that we make now this 10 minutes break so we can, as I said, collect all the information, collect all the videos we have recorded, make sure that we are not showing anything in a video. And so when we are back from the coffee break, then we will show this post-mortem analysis.
Thank you, Edu. Just would you like to have some questions first? Because there were a few that came up. So maybe we can have a short Q&A before the break.
This is indeed a very good question.
Okay, perfect. So I'm going to let you sharing your screen, and I'm going to ask the first question that came up. So there is a question that says, that's a general one. So it says, if you started the project from the beginning, what would you do differently from the city perspective?
Probably this you can answer.
Okay, I try to answer. For the city of Modena, a so challenging project like CLASS was a new experience. A very, very positive experience because we found a team, we create a team with other partner. So for us was a pleasure and was also very interesting to develop research and to provide new services to citizens. From my point of view, now I don't change anything in case of a new project or a new class 2 project. There is an element, a technical element. Now we have at disposal 5G network. So some issues, some problem with latency are naturally solved. Some features are easier to develop. But for me, for the perspective of City of Modena, the experience was great.
Great, thank you. That's very positive. So I have a second.
Let me comment also from a technical. So of course there is the point of view of the city, but also from a technical point of view, I would also like to mention something that I think if we would start the project now, we would do differently. And this is mainly because of the trend we are observing in the edge computing. So when we started this project, we assumed that the edge computing, so the resources, the edge computing resources were private to us. Okay, so we have full control of the edge nodes, and so we can do whatever we want. So the trend is it's more and more to try to not try to apply the same model in the cloud at the edge level, so that the edge resources are not really proprietary only of the city. So in this case, the control you have over the resources is limited. Okay, so something, and this is food for, of course, other projects, is how can we deal when the resources, especially the edge resources, are not as controlled as the one we have now. What if there are other entities that provides the services to the city by offering edge resources to the city? We have the city required to invest on them. In this scenario, we will not have control over them. How we can still provide these real-time requirements?
Great, thank you. Thanks, Edu. We have a few more that came. So the next question says, was the city camera also involved in this scenario, or just the sensors of each car?
Again?
Sorry. So I repeat. Was the city camera also involved in the scenario, or just the sensors of each car?
No, absolutely. There were in fact 3 cameras. So you are going to see, once we process, that from the point of view of the city, so because what we are going to show is the video of recorded by one of the cameras, that this information provides from the city has been computed by the city as well as by the cars.
Okay, perfect. And another one just came in that says, did you resolve the latency issues while exchanging data packages between the vehicles?
Okay, class. So this is a good question. Class was not focused on optimizing the latency. Okay, we have been focused on when you schedule. Okay, when you deploy your system and when you schedule your workflow, you do it such in a way that you minimize the impact of communication, and you minimize the execution time as well as the end-to-end response time either. But we have not been playing with communication, meaning we have not implement any specific scheduling at communication level. Okay, so no 5G technology, for example, has been exploited in the project.
Thank you. Thanks. And I've got a last question, I think. So that one says, are you using an existing data model, JSON, ARXML, and only adding some patterns, for example, timestamp?
So I guess the question is that if we are using some data model in XML or JSON format, I guess this is the question. Okay, so
yes, correct.
So yes, the answer to this question is yes. This is specific. This is implemented in Python. Okay, so the data model is implemented in Python, but it can easily be extracted as an XML or JSON. We initially considered to also use other type of more generic, let's say, data models. Hardware, for example, is one of those. But we found that there were certain limitations because we really, as I said before, we really want to have full control, okay, as to see up to which time we can really provide this real-time requirements. And so we decided to just check at it, but not using and use our own model. But if you check our model and, for example, the one that hardware provides are pretty similar.
Thank you. Thanks, Edu, for this. I think we can have a short break now. And there are a few more questions that are coming, but let's have the break now. I think it's a good time. And then we can continue with the rest of presentations, and I'm taking note of all the questions and we will make sure to answer them right after. So if that's okay with all of you, let's have a short 10-minute break now. So we have a short breath and we continue with the rest of the presentation. So stay tuned.
Thank you.
Okay, we're back, everyone. So thank you for staying with us and thank you for all the questions that came during this time. So I think I'm going to give the floor to Edu again. There you go.
Yes, thank you very much. So as I said before, we just collected all the information we got, okay, and what we are going to show is the result of the execution, okay? And then we will make a very brief live demo again with the pollution emission use case. So Ellie, if you want to share your screen, so you can share with the audience the result of the post-mortem analysis. Okay, so the execution was not as good as we expected. In fact, there are questions in the chat that are already somehow spotting what you are going to see now. So whenever you want, Ellie. Yes. So this is what has occurred. Okay. So this is slow because we are right now processing all the information all the logs we collect during this run that has been quite large. So you can see, for example, here that there is a car at this level that it is computed. The trajectories, the one in a roundabout. There is this car, the Maserati car, it is advancing. Sometimes the DNN detects, sometimes not. But what you are going to see now is, there has been we miss frames. Okay, so here can be because of two reasons. Can be because of the connection with the camera, or because of a saturation of the computing resources. This especially occurs at the beginning of the execution. So then what we are going to show, because maybe with this video you may have a bad flavor of a demo, and so what yesterday we did, I don't know, like 20 tests, okay? And so we are going to show you one of the tests we did. So Elia, if you want to start. So this is a video, a test we produced yesterday. So you can see that this time the two cars are collected, the trajectories are predicted. It is this red line you see, because the Levante is advancing very slowly. The trajectory is very small. The Quattroporte it's large, and you're going to see very quickly that a collision has been detected. Here you have, and then it just passes. Okay, this execution was done yesterday with 3 cameras as well. So it's exactly the same demo you have seen today, but this time with 3 cameras as well. Okay, so perhaps we can go quickly through the questions posted. There are a number of them. So, Nicoleta?
Yes, so let's start with the questions that came up also during the break. So the first one says, how to ensure that the data transferred back and forth is not lost or corrupted from vehicle to cloud?
Yeah. There are two. So the answer to this is, it is a trade-off between real-time and accuracy or on a data. So all communications are based on UDP, which means that we are not guaranteed. Why is that? Because what we really want is we want to stream data as fast as possible, and we process them, trying to guarantee real-time requirements. If we would introduce protocols that are more secure, okay, and guaranteed, the case when the package are lost, we would be losing. Okay, so this and those that are, and I see that are people from the audience are from the automotive domain. This is not a safety critical system at all. Okay, this is more a mission critical or a quality of service. And just to let you know, the latency we are observing, so the end-to-end latency we are providing, it's in the order of 100 milliseconds. So so this means that we can process 10 frames per second.
Mm-hmm. Okay, thank you. I continue with the next question that says, has the class project any comparative KPIs between classic scenario and edge scenarios regarding to data flow reduction, reducing latency, processing the data, etc.?
Okay, so if you recall my presentation, the introduction, our objective, one of the key elements we have been focused on is on the productivity. So how we can facilitate the deployment, so the development, deployment, and execution of work. Okay, we have focused, we have done our best in order to include the most advanced data analytics, but this has been not one of the cores, one of the main elements. And this is why, for example, there are some analytics that could be improved. So just to you know, what you have seen here, the DNN we have been using, it's YOLO 3, and YOLO 3 it's not the best one. So we could use YOLO 4 or YOLO 5 or YOLO 6. Okay. But this is something that, as a continuation of this project, is on refining the analytics of a workflow, so we can really move to the latest and the most advanced data analytics.
Thank you, Edu. I have another one that says, based on Maserati's overview of the sensor package, was the sensing or the perception sensor mounted on the car done from sensor itself, smart cameras, or the processing of the images and the clustering of LiDAR's point cloud was done completely with the cloud computation-based architecture?
No, everything has been done on the car in an NVIDIA Pegasus.
Mm-hmm. Okay, so that's answered. And there is one more question, but I think Roberto might kind of reply to that with his presentation that is coming up. The question says, how did you manage tracking with GDPR besides anonymous data? Do you track the object IDs to follow the development of a potential conjunction? Is this something you would like to reply now, or maybe Roberto will take it?
This is going to be addressing Roberto's.
Okay. So at this point, maybe we can finish this Q&A part.
Okay, so then let's just make a very quick, are we prepared for making a quick pollution demo? This is a yes or this is a no? Yes. Okay. So Ellie, whenever you want, you can share your screen again. So this is the other use case we were looking at. So we have developed this dashboard in which we are processing we are printing a pollution map of the area in which we are focused on. So as you can see, we are only spotting two parts, okay, that are right now the cameras that are activated right now and this is based on the exact same workflow you have seen before, okay, for determining a possible collision. We are obtaining the dynamics characteristics of the vehicle, mainly what is the speed and what is the acceleration, and based on this, we are providing what is the level of pollution emitted in this area. You can see that we are focused on different types of gas. We are focused on NOx. We can focus also on CO. So Ellie, can you show 1 second the gas type? And you see, for example, there has been refresh. This means that this is produced for now every 5 seconds, 5-10 seconds, if I recall. So we are gathering the information during 5 and 10 seconds, and we are generating an estimation of what is the level of pollution in real time. Okay, we can reduce this, of course, as much as we want, but in order to make it valuable, okay, we need to have gathered data in half a minute, one minute. Okay, and this is the other use case we would like to show. What you have seen today is live execution. So this the level of pollution right now in the city of Modena, in the Massa. Okay, so that's all from our side. So
thanks very much, Edu. I think we can wrap up the use case presentation at this point. We answered quite a few questions already. So let me share my screen now to share again the agenda very quickly. So we can continue with the presentation of Ereth Haddad from IBM. Ereth will talk about the class data analytics platform, deploying the big data analytics methods in the smart city. So we did receive a few more questions, but I think we will answer them with the next presentations, which are going to be on the data analytics platform, cloud, and edge computing as well. So they are all noted. Thank you very much to the ones that have asked questions already. So keep in mind, we will make sure to reply to those. So if Ereth is ready, I think we can.
I'm ready, Nicoletta.
With his presentation. Perfect. So the floor is yours, Ereth. I stop sharing my screen.
So hi, everyone. I'm Erez. I'm from IBM Research in Haifa. And I'm going to talk about the class data analytics, the big data analytics methods in the smart city. So let's see. Okay. So before so the purpose of this presentation is not really to bother you all with all the many technical details that involves the class analytics. What I really want to show you is just a few interesting highlights that have been learned and produced, some of which as lessons during the entire time of the class project. So I start first by showing you the direct application of these analytics in our main use case that Edu presented earlier, our V2X application of collision avoidance. So as you can see in this chart, there are quite a few analytics involved in doing the collision, in making collision avoidance happen. First, there are the sources of information. There are both the smart cars and there are the smart cameras deployed in the cities. Both of which are being used as sources of information, and both of them are actually already running analytics, which Edu already mentioned in his talk. For example, for the cameras, we are running one kind of analytics, which is the YOLO DNN. And for the smart cars, we have another type of analytics, which is the sensor fusion that's running on the cars. Both of these generate this stream, they take input that comes from various sensors and basically generate a stream of symbolic object representations of the entities running around in the massa, whether those are cars, pedestrians, bicycles, etc. Now, each of these objects is detected multiple times, obviously, when it's going through the various locations in the massa. As such, a history is constructed for each such object. Based on this history, we can now predict the future movement of that object. This is the trajectory computation that you see in the next square, done again on top of a lithops platform, which is also part of another analytics platform that is part of CLASS. Based on the computed trajectories, we can now estimate the possibility of potential collisions, future collisions between entities. And specifically, those that we're interested in notifying about, these are the connected cars. Connected cars is a larger subset that covers both smart cars and cars that just have a means of being notified, but not necessarily produce any information. So this computation comes in the next box, which you see at the bottom, which is filtering and collision detection, where we do both collision detection, but we do it on a filtered subset that pertains to the cars that later can be notified. So the result of this computation is actually collision notifications that can be later on sent to the cars. So how do we make all these various analytics communicate with one another efficiently? To this end, we actually have two means of doing so. One of them is they can communicate through the data backbone of CLASS, which is DataClay, shown at the bottom of the screen. The entire analytics is built on top of the comps and DataClay. Another means of communication, which we introduced, which allows more direct communication between components, is based on a serverless infrastructure. We use Apache OpenWhisk. I'm going to explain a bit more what serverless is in the next slide, but in the meantime, I'd like you to just grasp the general concept, where we have different components. For example, as you can see in the chart on the right side, we have a MapReduce components using lithops. We have a workflow components based on comps. We have DNNs. We may have a complex event processing component. They all communicate with can communicate with one another directly using the serverless platform. And how is that? This is done by having the application deployed as a set of serverless functions, and then these functions can be either invoked directly using the serverless protocol or be bound to various events such as network events, sensor events, user input, or timer events, all of which are actually uniformly handled through the serverless protocol, causing invocation of the said analytics backend, and thereby causing a response by computation. So what exactly is a serverless? What exactly is a serverless platform? So I'm just going to give you a very, very short example. So when you do serverless programming, you basically start by writing a code function, an actual code function. In this example, I'm showing a JavaScript example. You just have a function that takes a parameter of a string and returns another string based on the input parameter. Okay, and then. But this function has meaning only for in the context of a JavaScript application. However, we want to invoke it globally using the serverless protocol. So to do that, we convert that code function into a serverless function, which is actually a microservice. And we do that by using, in the case of OpenWhisk, we use the whisk command to convert it to a globally accessible function. Once this is done, we can now invoke this function just as we would do inside a JavaScript application, only now we can do this from any kind of application using the standardized serverless protocol. So here you see an example of this function being invoked, but not only that. We can now take the same function and invoke and bind it to events. We can create an event trigger. We can bind the same function to that event, and then any kind of event that happens on this event trigger, it's kind of a pub sub channel, will cause these function to be invoked. And as I said, going back to my previous slide, if this function happens to be a computation of lithops, a computation of comps, a computation of DNN, that computation happens in response to the event. And the magic of serverless is actually removing the need of the developer from messing with the infrastructure. That's actually the reason for the name serverless. You don't deal with the infrastructure, you don't deal with deployment. And furthermore, and as many events as are generated, so are as many function instances are created to handle those events. This is auto scaling, again, handled by the platform. So there is a bundle of advantages here that really play directly to one of the core premises of Class, which is developer productivity. It's event driven. You can respond to event. You can do direct invocation, auto scaling. The deployment of the function instances are actually isolated, which means you can deploy it on shared infrastructure safely, such as a commercial cloud. It's lightweight enough to fit both on edge nodes and on cloud scale. It's polyglot, so you can deploy in many different programming languages and frameworks, and it works with rapid prototyping. But here is the interesting tidbit, because Class is all about the applications we're talking about. It's about real time. It's about low latency computation. And in this case, we realized there are a few shortcomings of the serverless platform. One of them, for example, is that serverless functions are naturally stateless. Why is that? Because a serverless function is spawned out of the blue in response to an event. It doesn't know anything of the application context so far. So how do you make it aware? So one way to do that is passing information through parameters. That's a common mitigation. Another mitigation is to use the underlying data clay backbone and have the function retrieve information from it. But this actually leads us to the next issue of serverless platform, which is initialization and finalization overhead. And this is the cause. First, a built-in issue with serverless platforms is the so-called cold start. When you spawn a new serverless function running in a container, that means a new container has to be created on demand, on the spot, populated with code. You pass the parameters to it, and then it starts executing. All of this takes time. This is just infrastructure overhead. And even after this happens, then there is the application overhead. Let's say our function needs to connect to data clay. That means it needs to open a session and communicate with the underlying data clay. And that also, opening a session also takes time. So this is application overhead. Altogether, this might take a significant amount of time, which kind of is counterproductive when you think about real-time response for events. So how do we mitigate that? One common technique we leverage is so-called warm start. How do we do warm start? Essentially, most serverless platforms, when they create a container that executes functions, they keep that container for some time more in memory after execution is complete, because of the chance that another invocation might happen, and they leverage the container that's already in memory, thereby avoiding the cost of cold start. So we actually leverage that intentionally by adding rounds of warm start throughout the execution. Another issue is finalization. Often after the result of the computation is already created and committed, the function still needs to update some statistic, generate some logs, close sessions. Again, that adds more time. So one way to handle this, and this happens in lithops, which is my next highlight, is we use asynchronous execution, meaning we let the function execute and we wait for the result to appear as opposed to waiting for the function to complete. And that often saves a lot of time. And then the last aspect is scheduling. You're taking a pre-made, if we're taking a pre-made serverless platform such as OpenWhisk, it comes with its own scheduler. It comes with its own control of scaling, which means that you have to use what you have. But this is This may be inappropriate for some use cases, such as real-time response. So how do we do that? One mitigation is warm start, because once you get the containers in memory, you've already passed the scheduling point. But another mitigation we often had to do is actually go down to the core of the system, whether it's OpenWhisk or the Kubernetes cluster it is running on, and actually tune them manually. So that was serverless. The first item was serverless fabric, and especially in the context of class. The next item, again in the context of class, is one of the backends. I'm going to talk about specifically about LithOps and how we tuned it to do low latency computation, again to meet the requirements of class. So what is LithOps? LithOps basically is a Python library that can be integrated into applications, and it allows massively parallel computation. It is basically a MapReduce engine. What is a MapReduce engine? Many of you are probably familiar with it from Spark, from Hadoop, from Flink. It provides two core primitives. One of them is the map primitive, which takes a function and a data set and basically concurrently applies the function to every element of the data set, yielding a new data set. And the other is reduce, which is similar to map, only it involves an accumulator, so that the result could be a sum, an average. It can be a single result, or in the general term, a different size data set. So why would you use such an engine in the context of class, in the context of real-time computation? Because of parallelism. The basic concept holds true basically in any execution environment. The more parallelism you have, that true independent computation, you can get lower total latency, but for processing more data. So this is exactly how LithOps operates, and you can see that in the bottom of the chart. The client code calls the map operation. Then what LithOps does, basically, it takes the data set that's provided as parameter, identifies all the elements, and issues independent invocations to each of these elements. Then we switch to the right-hand part, and there you can see when it's running on OpenWhisk, and let's say in this tiny, very trivial example that I'm showing you on the slide, we have a concurrency limit of, let's say, up to 4 concurrent functions. Then basically this is the behavior we're seeing, like 4 concurrent repeating rounds of execution. So we observed this behavior, and this was not good enough, because we have some timing goal, specific timing goals that we need to meet. So just letting it run best effort is not good enough. So what we did is we took it and we heavily optimized it for the class use case. One of the most important observations we made is that when we talk about big data in class, we are actually talking about a very large number of small elements. A very large number of small elements, we can optimize the communication in LithOps to work much better for this use case and thereby gain a specific speed up. So what kind of communication? What kind of communication was it? So for example, one of the core foundations of communication in LithOps between the client and the workers involves using object storage, which is good for large, heavy elements, but really becomes a kind of an overhead when you use small elements. So we were able to optimize that protocol and take the object storage out of the equation, thereby significantly speeding it up. Another important aspect was we sped up the launch of the workers themselves. And then finally, one of the very important improvements was avoiding this round behavior that you're seeing here in OpenWhisk. Instead of having this is a typical case, what happens when you have a lot of data elements and your concurrency limit is relatively small in comparison. For example, let's say you're allowed to run 1,000 concurrent functions, but your data set consists of millions of elements. In that case, you need to what you need to do is basically start at the same functions over and over again, pay again the cost of starting and stopping each function invocation just in response for, and not just one more data element. So what we did that we identified that by chunking data elements together, we can get a significant speed up. So the overall result of the total optimization, for example, was one of the V2X cases. We reduced the total cost of trajectory prediction from 4,000 milliseconds to less than 350, over 11.5 times. The last highlight, I know I'm a little behind time. I'm at the last item. So the last item I'd like to talk about is how we make class analytics universal, because class is supposed to work across the entire continuum. We're supposed to have analytics running the same way, both in the cloud and in the edge. How do we make that happen? Because edge nodes are significantly different from cloud nodes. They're only loosely connected to the cloud, and they have their own scheduling. They're actually independent instances, and communication between edge and the cloud is not always reliable. So how do we give the same developer experience over a uniform platform where we have that loose interconnection? So the way we do it is by employing federation. Federation is a system we built on top of OpenWhisk that allows us to basically propagate software assets from one OpenWhisk instance that we say, for example, running in the cloud, to multiple OpenWhisk instances that could be running in edge nodes. The origin is where we deploy the assets is called the leader, and then the targets where the assets are propagated to are the followers. The leader and the followers, of course, can be any OpenWhisk instances. So it doesn't have to be a cloud and edge. It can be also a multi-cloud scenario. But the idea here is that each follower, OpenWhisk basically becomes a programmable agent of the leader OpenWhisk. So what happens is, if we have a kind of an application that is deployed as a set of OpenWhisk functions, you deploy it in the cloud, you just press federate, and that entire application is propagated in an eventually consistent manner to all the designated edge nodes. So, and this is actually the main use case for federation. So basically we're keeping the same user experience. However, federation is applicable also to non-OpenWhisk assets, which I'm going to show in actually my near last slide. So this is a joint work we did with one of the partners, with Unimore. We took the so-called class edge application. This is not a designation of a specific node. It's actually a name of an application that needs to run in the edge. A class edge is not an OpenWhisk application. It's actually a long-running stateful Docker service for edge nodes. Yet we were able to use federation to propagate it to the edge nodes, the very same mechanism. How did we do that? So one cool feature about OpenWhisk, it has this capability which we call project manifests. Project manifests are actually containers of data that are considered open. The container itself is considered an OpenWhisk asset, so it can be federated. So the way we do it, we put the new Docker the new version of the Docker application in the Docker registry. We create a manifest that contains the tag of the new application, and then we federate it to the edges. And then the opposite end of the federation, which is constantly running in each of the edge nodes and monitoring for updates, picks up this update and then knows it's a Docker container, pulls the image to the edge node, and make sure that the service is degraded gracefully and started afresh with the new version. And to summarize my talk, so basically, as I said, I presented three main highlights involving class analytics. One is the event-driven serverless infrastructure based on Apache OpenWhisk, which is cool and productive and extremely easy to use. It's polyglot, auto-scaling, simple. But we needed to do some changes to make it work for class when we're doing low latency invocations. Okay. The second aspect I discussed was that how we took one specific backend, such as LithOps, and adapted it to do low latency computation. and where we employ parallelism, but it needs significant optimization to match the really low latency requirements of class under the constraints of class of big data consisting multiple small items. And finally, I showed you how we use federation to make the class analytics span both cloud and edge. Thank you very much for joining us today and joining my talk.
Thank you.
I will now take questions and answers. So
thank you, Erez. Yeah, thanks very much for your presentation. That was very interesting. Because we are running a bit late, we did receive a couple of questions on reducing latency, but I'm thinking that it's better to collect them all together and let's answer them during the Q&A slot that we have at the end of the event. So thanks again very much for your presentation. So maybe we can continue with the next one. That is the presentation of Ruth Palmero from Atos. Ruth is going to talk about the class cloud computing, guaranteeing service management and performance. So Ruth, let me allow you to share your screen. And are you sharing your screen now?
I will share my screen. Yes, thank you, Nicoleta. And thank you everybody for joining us today. I just wanted to say, because today is the last day of the project and that Atos couldn't be there in Modena with you, that it has been a pleasure for all of the people that throughout the years has been part of this project to work with you. So let me share my screen now.
Perfect.
Okay, I want to display like this.
Yeah, if you go to configuration.
Yes, but I have another and not okay. Oh, now.
Yes.
Okay, finally. I have it.
No, we still. Now it's working. Okay, perfect.
Now it's okay.
Go ahead.
Okay.
Perfect.
Okay, let me minimize some things. Yes, so well, I'm going to talk about again the class cloud computing continuum and how we have worked to guarantee service management and performance. Mainly, we will describe Rotterdam, our container as a service element, and also the SLA Light, that is the component that we use to enforce the quality of service. We will also see how we have improved the SLA to guarantee time, to provide time warranties. Okay, Rotterdam, as I say, is a container as a service. It allows deployment and management of containerized application in the Modena data center. We have a cluster, Kubernetes cluster, and it is able to deploy COMPS workflows. It supports also the management of multiple infrastructures like Kubernetes, OpenShift, Micro Kubernetes, Kubeless, and so on. And it can, other than the COMPS workflow, it can run applications and also some functions applications on the cloud to edge continuum. It has inside the Rotterdam, we have the SLA Lite. It provides the possibility to refine quality of service rules that controls the scalability and the elasticity. It's very easy we have a single JSON format for describing both the general application that needs to be deployed and also the different quality of service rules that has to be applied to the tasks. And we have a REST API interface to communicate with Rotterdam. So what we have in the Modena data center, we have two Kubernetes clusters. We have our private cloud. One is an OpenShift cluster, another is a Kubernetes cluster in which Rotterdam and the SLA Lite are running. So initially, the application will be defined a simple JSON file in which describing, as I said, quality of services and the definition of the workflow. It will transmit it to Rotterdam that will deploy the application or the workflow in any of the infrastructure, either in the cloud or in the edge. And it will actually communicate with the SLA Lite. It will create an agreement of a quality of service agreement and make sure that the quality of service is being met. So the time that it is not being met is when it will scale out or in the tasks, the workflow tasks. So this is an example first of what is the JSON file to define the execution of a workflow, so of a comps workflow. Initially, 2 replicas needs to be created. Later on, my colleague will define what is comps and then what is the terms of replicas we can consider right now as workers or pods or elements that run in parallel. And it also defines in the JSON what is the type of application that is going to be needs to be developed, and the quality of service by a level. Okay. Also, it can be another type of application, workflow, serverless functions. So the JSON file to define the application is quite easy. The SLA Lite receives also this JSON from Rotterdam, and it creates the SLA agreement. In the SLA agreement, it is defined what are the constraints that has to be met all throughout the execution of the different replicas. And in this case, the initial number of replicas is 4. And in case of a break of this constraint, that is a deadline miss. Deadline miss is actually like the time to execute this task is not going to be met, something like that. So the Rotterdam will make sure that there is an escalation. It will scale out to 1.5 replicas. So from 4, it will move up to 6 replicas. So this will be the flow of the execution, right? The application is pushing the information of the deadlines into the monitoring, and the SLA is actually from the monitoring obtaining the information to supervise the meeting of the quality of service of the SLA. Okay, the time it is not being fulfilled, then Rotterdam will make sure that it is going to scale to the number of workers that were defined in the agreement. So we perform with a short comps workflows. This schema is working and it guarantees the time of execution. But we have realized that when the execution lasts longer, there is an overhead of the scaling itself. So from the time the deadline miss is identified, since the time the workers are contacted, the new workers are launched, comps is again starting the execution with the new workers and so on. This time it presents an overhead. So what we thought is what we could obtain a prediction of that could help us to guarantee the time of execution. So initially we have added, actually, we have changed a little bit the way in which we define our quality of service. Is not the deadline missing anymore, but we have the number of replicas and the value of the final execution time that is desired. This is what is being provided in the JSON file. And we have defined a new component that is the SLA predictor. It's actually a machine learning. And what we expect from it is, okay, we have the desired number of replicas and value of final execution time, but will it be from previous executions? Can we assess that this is going to be possible to have this execution with this number of replicas? If not, we can immediately launch the more efficient number of replicas with, and like that, avoiding the need to scale later when the deadline miss has to happen. So the SLA manager, when it receives the initial quality of service rules, the conditions, it will actually ask the SLA predictor if this will be possible to be met, right? This is a machine learning, and if not, it will actually give the actual number of replicas that is optimus for this execution and in this execution time. And like that, we avoid to have to scale from 4 to 6 replicas. So how did we design the SLA predictor? Well, we classified the state of the system, the state of our cluster, our Kubernetes cluster. We did an exploratory data analysis, and we classified. We actually did a classification training model, and we classified into low, normal, and high levels. So depending on these low, normal, and high levels, and also the desired time of execution, we obtain the expected, the better number of workers to be used. So actually, we implemented the model training into a microservice with a REST API, and what the SLA does is that it asks if with 4 workers and an execution time of this, it's possible to finalize the task. And if the output is 6, it means that the number of workers cannot be 4 but 6. And like that, we immediately, from the very beginning of the execution of the workflow, we have predicted what is the ideal number of workers that will finalize the job. And that's how we avoid to have to scale. Yeah. So just to summarize, I have explained how we have Rotterdam for the deployment and lifecycle management of containerized applications, that it works on multiple infrastructures, that it has a simple REST API to communicate with it, and a simple JSON format to describe the application, and that it provides the possibility to define the quality of service rules for scalability and elasticity. And we have also described how we have improved the SLA prediction with the SLA predictor, our Rotterdam, to try to provide more time warranty, and like that, our application scalability and elasticity will be triggered by informed quality of service rules. And well, we have an initial training of the model to obtain what is the classification of the system in terms of uses of resources before obtaining the actual real state of the quality of service that is Optimus. So, well, that's all. I think I can have some time if you have some questions.
Thank you, Reth. Thanks very much for this. So we are running only a slightly bit late. So if there are no questions at this point, I think again we can move on with the next presentation. So let me share the agenda once again. Okay, thanks. Thanks, Ruth, again for your presentation. So maybe we can go ahead with Roberto's presentation so we can continue with the technical aspects of the project. This is a presentation of Roberto Caviccioli from Unimore on the class edge computing layer, so AI infrastructure applied to smart mobility. Let's continue then with Roberto's presentation, and as I said before, feel free to write your questions in the chat or in the Q&A function. I make sure I collect them all, and we will have enough time to discuss all of them during the Q&A slot that you see here. So if Roberto is ready.
I'm ready.
Perfect. I can give the floor to you. So I'm going to spotlight you again. Okay, that's great. So you can begin whenever you're ready, Roberto.
Okay, thank you very much, Nicoletta. So hi everyone, and thank you for joining us. My name is Roberto Caviccioli. I am a researcher here at Unimore, and now I will talk you about the edge analytics that we have deployed inside the class software infrastructure. In particular, the need of these analytics was to be able to implement our use cases. So what is our main target? The target, as you have seen in the demo this morning, is to have a real-time obstacle detection and collision prediction that will send warning signals to smart vehicles, connected vehicles, and so on. So just to clarify for us, the connected vehicle is just a vehicle that has a GPS, and it could have a small embedded board like, I don't know, a Raspberry Pi, an NVIDIA TX2, whatever, that is able to send to the infrastructure via a 4G private connectivity that we have, low latency communication about its own position. While on the other hand, the smart car is a car that also has sensors such as cameras, lidars, and so on, that we are able to fuse to obtain the correct position, not only of the car, but of all the other road users that are around the vehicle. And since our software infrastructure is scalable, as shown previously, we imagined 5 different scenarios to be run. You have seen one, but we were able to also test and verify also the other tests here. And we have divided this kind of scenario into 2 different functionalities. One is the virtual mirror. What does it mean? That I am not able to see anything, but the city sees for me. The other one is the 2 sources of attention, which is like I am too focused on one side of the road because there is an incoming car or something like that. And on the other side of the road, something is happening and I'm not able to assess the risk that there is incoming. So for the scenario for the virtual mirror, here, for example, we can have 2 city cameras in the Attiraglio street and a detected pedestrian and the smart car. In this case, we can have, I don't know, a truck or a bus that is hiding the pedestrian that is crossing the road. While on the other hand, even if we have a smart car, the sensors are not able to detect what is behind the car, truck, or the bus. And therefore, the city will be the virtual mirror for the car. And since the pedestrian is crossing the street, the sensors of the city, so the cameras, are able to detect it, provide its position, provide its trajectory, and therefore warn the car that there is a pedestrian in its own trajectory. On the other hand, the car is not able to detect and see the pedestrian on their own. The other one that you have seen this morning is actually the 2 sources of attention, because we have the Levante car that is exiting from a parking lot. While it is exiting, there could have been a pedestrian on the right-hand side before going inside the roundabout, and therefore the attention of the car might be focused on the pedestrian. While on the other hand, the Quattroporte car was approaching the same roundabout and going to cross the path of the Levante without any attention to that part of the road. So here, an alert can be raised from the city infrastructure to both the connected vehicles, because the Quattroporte maybe couldn't be able to detect the car that is exiting from the parking lot, but since there is the camera that is seeing exactly the exit of the parking lot, that is detected and sent as an object, let's say, to the smart car. And on the other hand, for the Levante car, we have the warning for the approaching Quattroporte and for the crossing pedestrian. And to actually be able to run these kind of scenarios, we need the analytics. Some of the analytics have been already discussed by Erez previously, and now we have to discuss how we are able to detect the correct position of each object inside the Masa. So the first thing that we do is that we detect all the possible road users, which can be cars, pedestrians, bicycles, buses, car trucks, and so on. Being able to detect this, then we obtain the bounding boxes on the camera image. Then from these bounding boxes, we can obtain the GPS position of the object. Why is that? Because we can assume that the lower part of the bounding box is where the object is touching the ground, and therefore the plane of the ground can be converted with its own GPS latitude and longitude with an homography matrix to the correct GPS. And then what do? We have somehow to track, to obtain what is the trajectory of each object. And to do so, what we need to do is to convert these 2 meters to be able to assess, speed as meters per second or something like that. And therefore we convert from the GPS to the meters in a different in a different coordination system to be able to also feed our tracking to be able to assess what are the different trajectories of all the objects. For detection, we use neural network. In particular, as also Eduardo said this morning, we are using YOLO. You only look once. YOLO is, let's say, the state of the art with respect to detection network. And detection network, it means that when I have an image, I'm not interested in assessing if that is an image of a dog or a cat. That is classification. Detection is where is the dog, where is the cat in my image. So to assess where the dog or the cat or other objects are, the image is, in the YOLO algorithm, the idea is to distribute the different parts of the image inside the network to assess for each part of the image, how is the probability of that part being of some category with respect to others, and then to join the different categories with the different areas to obtain the final detection. And as of now, YOLO has been evolved. There is, as Eduardo said, we do not only have YOLO versus 1, we have versus 3, versus 4, and so on. But we modified YOLO. Why is that? Because we needed speed for YOLO. So YOLO is implemented in C++ and also in Python, but what we needed to do was to accelerate it to be able to run on GPU. Why? Because our edge and fog nodes are GPU capable devices. And therefore we optimized our YOLO using TensorRT, and we have published this as TKDNN, which is an open source project inside class. Also, we retrained YOLO. Why is that? Because YOLO is usually trained, the base one, on the COCO dataset. COCO is a dataset from Microsoft that has inside 80 classes of different possible objects. We are not interested in cat or dogs. We are interested only in cars, pedestrians, and so on. Therefore, we retrained our network on 2 different datasets. One is the UAD-track dataset, which is a Chinese dataset that contains images from street cameras, which is exactly how what we need for the street cameras in our city. And on the other hand, for the point of view of the car, we retrained on the BDD 100K dataset, which is the Berkeley dataset. And this dataset contains segmentation and detection of objects that are from the point of view of a smart car. And therefore, we have trained many different versions of YOLO to be able to provide the maximum accuracy in the detection for the different use cases that we are solving. And we have different performances. Since in class we are interested in real-time capabilities, we have to be sure that the version of YOLO that we are using is not overpowering our device, or at least that it responds to our device, to our request, the real-time request, in a suitable time. As you can see here, the different versions of YOLO that are present provide different capacities of frame per second computation. But if we go to the highest frame per second that is in the YOLO version 2 trained on the Berkeley that we have here, you see there are lower precision on the detection that are in the rows below about the people, the car, the trucks, and so on. While on the other hand, the highest precision is given by the YOLO version 4 trained on Berkeley. But as you can see, the number of frames per second that we are able to process at full precision or even at half precision is only 7.2 if we are on an edge node, let's say a TX2 or something like that. So to be able to use the best possible trade-off between a very good detection and a very fast computation, we had to choose correctly. And that's why we were using the YOLO V3 in our demo before, because as you can see, YOLO V3 is able to run at 10 to 12 frames per second, depending on the precision that you are using. But the maximum a priori, so actually the capability of the detection and the precision of the detection is between the best of the YOLO V4 and the worst of the YOLO V2. And as you can see, COCO goes very well on person, but drastically drops on everything that is not a person. So this is the result of our detection. As you can see from a camera, we can run at 12 frames per second. And as you see, we detect all cars in green, a person in purple, a truck in yellow in the background, and so on. While on the other hand, while we are on a car, with a different network that we have trained there, we are able to detect better all the objects that are at the same height of the camera, instead the camera being on top. And we can also detect traffic signs and other stuff that might be useful for the ADAS system that are on top of the car, but these are not useful for our use cases because we don't care if there is a traffic sign or not. We are just interested in the position of all the road users to be sent to the infrastructure. Then we talk about tracking, because we need to track the object to be able to perceive their path and to predict their path. So what do we do for tracking? We filter every object using, as we said, the lower center of the bounding box to be able to see, okay, this is the place in which the detection says the object is touching the ground. Then we use an extended Kalman filter. The extended Kalman filter is a Kalman filter, which is a mathematical filter to smooth the path that we are detecting. And then we use the nearest neighbor technique to associate the bounding boxes of the same object between an object in a previous frame and in a successive frame. Why is that? Because, as someone was already requested, we track with IDs, but we do not take these IDs into memory. We will explain this also a bit later. We compute one tracker for each object that we detect. So we have multiple trackers for each object that we detect in our view. This is from a camera. As you can see, behind the car, there is a trailing road, a trailing line of points, also behind the pedestrian. And each color that you see of the trailing points is a different tracking. It means that sometimes if we miss the detection for some frames of an object, that object is not anymore the same object as detected before, but we are able to re-detect the object and restart a new tracker to obtain the path and the prediction of the possible path of the object. Also, the same thing, you can see what we do. We obtain this tracking, these paths, and we are able to re-project them onto the GPS position that we have in our city. So to be able to correctly position each object in its own position while we have to send this information to our connected cars as smart cars. And what is the performance of this tracker? Well, extended Kalman filters are really, really fast. On our edge node, since we are also able to parallelize this on GPU, we are able to have about a 3 millisecond computation for computing the trajectory and the tracking of 80 objects, while on a mobile edge node, which can be a TX2, a PX2, a Pegasus, and so on, we usually take 10 milliseconds to track 80 objects. But that's okay, because all of this is inside our end-to-end latency computation, and with respect to other kind of computation, this is very, very, very small. And then anonymization. Why do we have to talk about anonymization? Because we are under GDPR rules. Since GDPR is very strict about the knowledge of any kind of information about the people, about whatever we see in a video, what do? Then we just record the position of object without the ID. What does it mean? Whenever we detect an object, we translate that object as a record with no image recorded, and we have the time, the position of the object as latitude and longitude, the category of the object, so we only know that there is a person, a car, or a bicycle, or something like that, and the predicted path at that point in time, so the orientation and the speed of the object. We don't actually record. You have seen this morning in the demo that only for debugging purposes we are doing that to be able to ensure that every object keeps the same ID if detected from a certain camera. But when we pass messages between our software architecture, any of this information is not stored, and also in the aggregated time, this information is even lost for a single point, because when we aggregate temporally, we only have the average number of person, the average speed, the average number of car, and so on within 1 minute, 15 minutes, 1 day, and so on. Therefore, we are compliant with GDPR and privacy needs of our citizens. To convey this information to the different cars and obtain this information from the cars, we deployed also, as was said before, a UDP message protocol. Since we wanted to have the lowest latency possible, we compressed the information to be a binary information. So we weren't able to use something like XML or JSON because they are verbose. And therefore, due to the low latency and low bandwidth that we have with our private G connection, we had to use binarization. To binarize all of this information, we were able to assess that 50 to 100 objects that are detected inside the MASA only take less than 1 kilobyte of memory to be sent over 4G as a packet of data. And then that packet, even if it is, let's say, intercepted by a malicious attacker, is not able to be reconverted to information because it is compressed and binarized. And if no information about how the compression has been done, there is no way of obtaining back the data of each single node. And that's it. So.
Thank you. Thanks, Roberto,
for
your presentation. I do have a question for you, which I mentioned earlier. I think you largely covered it already, but I'm going to ask it anyway in case you want to add something more. So the question says, how did you manage tracking with GDPR besides anonymous data? Do you track the object IDs, meaning to follow the development of a potential conjunction?
Yeah, exactly. So we track the object ID and we keep the object ID in memory only during computation because we need to assess that the object is still the same to predict the position of the object in the future. So we only keep them while we are processing, but we do not store them. We only keep them and send the predicted trajectory in real time, but we do not store the predicted trajectory or the previous trajectory of the object, because that is only done for us for the debugging project, for the debugging of the software architecture project. While when the car receives the data, it's only the warning of a possible collision, but there is no information also about that collision if it is with a pedestrian, a car, or something like that. We only communicate that there is a possible collision, so a warning, without the need of sending any other kind of information that might disclose the source of their data.
Right. Thank you. Thanks, Roberto. So thanks very much for your presentation and for answering this question. I think we can move on. Let me again share my screen, share the agenda one more time. So we can continue with the last technical presentation for today. This will be presented by Eli Karchakli from the Barcelona Supercomputing Center. And the title of Eli's presentation is Class Software Architecture, Efficient Execution of Real-Time and Advanced Mobility Functionalities in the Smart City. So whenever you're ready, Eli, you can start your presentation, and as I said, keep sending your questions in the chat or in the Q&A function of Zoom, and we will discuss them all during the longer Q&A slot we have right after the presentation of Eli. Okay, perfect.
Hi, thank you, Nicoleta. So my name is Eli Karchakli. I am a senior researcher at the Barcelona Supercomputing Center. And what I will present is the class software architecture, that is the architecture that brings together all the components that we have described so far and is responsible for the deployment and distribution and execution of the real-time advanced analytics that we have developed. So to begin with, I would first like to give you a quick overview of the challenges that we are facing and the need to develop a novel software architecture. So first of all, our objective was the distribution of the workflows and their execution. So distributed computing has been around for a while in the sense of distributing the computation over a shared pool of resources, for example, in clusters. But recently, with the advances in cloud computing, telecommunications, and networking, we have been shifting to the edge computing paradigm. So there, the big picture is that we have a layer of sensors, for example, IoT sensors, the smart cards that we have here in class, the network of smart cameras, etc. And all these sensors generate information. And sometimes they have some limited processing capabilities. Then we have the edge layer, that is where some computation takes place close to the data sources. And then we have the cloud layer. So all this pool of resources, we call them the compute continuum that spans from the edge to the cloud. And our aim is to be able to execute and distribute all the computation across the whole compute continuum. Now, there are several challenges in that, because first of all, we have to deal with a massive number of heterogeneous resources that are also geographically distributed. So in our example, we have a network of cameras across the city, we have the smart cars that are moving, etc. So if we want to keep the computation close to the data sources, and the data sources keep moving and are heterogeneous, this is a challenge. The second challenge is that we have heterogeneous networking. So as Luca already presented, we have different types of connectivity. We have wireless, we have the 4G network, we have fiber optics, we could have 5G in the future. So each different type of communication comes with different capabilities in terms of throughput, in terms of latency, and in terms of reliability. So then finally, we also have heterogeneous computing resources. So heterogeneous in the sense of computing and storing capabilities, in terms of architectures where we can have GPUs or CPUs, and in terms of operating systems. So it is very challenging for a developer to design an application, data analytics that can run over this highly heterogeneous infrastructure. And it's very challenging to distribute this workflow and make sure it is executed to the right place in this whole compute continuum, so as to ensure the real-time guarantees that are needed by the use cases. So this is the novelty that is introduced by the class software architecture. So I will just do a very quick overview of the whole picture of the class software architecture. So here you can see the different components that have been already presented by my colleagues. So first of all, we have the data analytics platform that has been presented by Erez with the serverless framework of Espresso and OpenWhisk, and the different analytics backends that are supported. For example, the MapReduce-based Lithops and the task-based Comps API that I will present later. And then we have the compute continuum, where we have the cloud components already presented by Ruth, and the edge software components that were previously presented by Roberto. And the missing link for all this is the computation distribution layer, that is where the Comps framework that I will present lies, along with the data clay that is a distributed data store responsible for handling the data transfer wherever they are needed. So the main contribution of this software architecture are that it facilitates the development of the complex data analytics, handling all this heterogeneity. It handles the distribution of the computation across the compute continuum, supporting the concurrent execution of the different analytics whenever possible. And also it supports interoperability, scalability, and portability. So let's see how our complex data analytics are executed over the class software architecture. So if you see here, at the left part, we have the data sources, which are the cameras and the smart cars in the case of class. Then we execute the object detections at the edge components. And then in the fog nodes that we have at the city of Modena, at the Massa area, we execute the rest of the real-time functions of the workflow, which is the object tracking, the deduplication, and then the creation of the data model where the information is generated, and the federation of this information to the cloud. And then at the Modena cloud, we also have the execution of the two different use cases. On one hand, we have the OpenWhisk cluster executing the list of tasks of trajectory prediction and collision detection, which then generate the alerts. And we also have the air pollution use case that is executed over the cloud components. This transfer of data from the fog nodes to the cloud is handled by the data clay. So here is a mapping of this workflow I just presented with what we saw earlier in our live demo. So here you can see the workflow of the fog nodes. So as Roberto already presented in the previous session, we have the object detection that in this image is represented by these blue boxes around the detected cars and vehicles. And then we have the object tracking, where the different objects are tracked across consecutive frames. And this results to the position of the objects that are represented by these green dots. Then we have the deduplication of the input from the different sources, for example, the 3 cameras that we have in the demo, and then the creation of the data model. And this results to the generation of a snapshot. So snapshot is just a data structure where we describe everything that has been detected on this frame. So in fact, we have all the different objects. We have an object ID that later will not be stored due to anonymization. We have the type of the objects, etc. And then for each type of objects, for each specific object, we have a history of events that correspond to the detected position and velocity, etc. of the object, of the same object in consecutive frames. So then the next step is to pass these snapshots to the cloud. So from the fog nodes, this information is passed with the help of DataClay to the cloud, where we have the data knowledge base that keeps a record of all the different snapshots along the execution that of course are periodically erased whenever needed. So then the data stored in the data knowledge base that are the output of the workflow presented before are then passed to the trajectory prediction function that calculates the predicted trajectories of the object that have sufficient history. So these predicted trajectories are then updated in the model and then are passed to the collision detection function. So the collision detection will make an estimation of all the possible collisions and generate the alerts that can be sent to the car. So this is the final output where the trajectories are marked by the red lines, and the different bullets, the red bullets, are the estimated trajectory in the next 500 milliseconds. And then we have the detected collision. So how do we go on to develop this type of application and distribute it over the compute continuum? So the first thing to do, this has been done in class using the COMS framework. So COMS is an open source framework for the distribution and execution of analytic workflows. And it can be found in the link I pass here. So the first step is to develop the sequential code in any typical language like Python, Java, or C. So for example, we have here the different functions to get the detected object from the TKDNN, to track them, to duplicate them, and then create the data model and send it to the cloud. And we have a loop where we access all the available sources, we do the detection, the tracking, and then we duplicate, etc. So how do we transform this sequential workflow into a distributed workflow? So with COMS, this is pretty easy because we just need to annotate the tasks to be distributed with a specific decorator, this task, and mark their dependencies. So we just go to its function declaration, we put this, delimiter, and then we explain the dependencies. For example, the tracker must receive the frames from the detection and must receive the track position from the previous frame. The deduplication must receive all the tracked information from all the trackers that are referred to the same timestamp, etc. So once we do this preparation, then our sequential program is converted to a parallelized program. And another key point is that this is agnostic to the underlying infrastructure, in the sense that we don't need to take care of where each task will be executed, because this will be done automatically by COMS. And I will show you how in the next slides. So when we do all this coding preparation, what COMS does after is that it generates the task dependency graph. So this is an example of the task dependency graph for 2 consecutive frames of the same camera. So as you can see here, we have the different tasks that are generated, and the lines between them are the dependencies. For example, we see that we have to detect first the first frame and then the second, marked by v3. And of course, this gets more complex as we add more sources. If we get a second camera, we have the detection and tracking of this camera that then will be duplicated jointly with the other one. So it becomes more and more complicated. And if we wanted to see the task dependency graph of 1 second of processing from a single camera, it would look like this. And take into mind that in class we have up to 16 cameras. So this is fairly complicated, but the developer does not need to handle this complexity. This will be distributed by comms. So once we make all these declarations, the next step is to take care of the deployment. So in order to do the deployment, all we need to do is provide a configuration file, an XML file, with the available computing resources. So in our example in class, we have the different fog nodes, 4 fog nodes in particular, that are Dockerized. So we launch the master because comms has a master and worker architecture. We launch the master gets this configuration file, and then automatically deploys the workers. And if we want to connect to the cloud where the Rotterdam cluster is also deployed as described by Ruth, we can do that through the same configuration file by putting the specific configuration for this Rotterdam API. So once this deployment is complete, then the master will distribute the different tasks wherever needed based on the scheduling policy that is implemented. And then at the time of execution, the task will be distributed and executed in parallel whenever parallelism can be supported. So this is a simple example from just execution of at one worker with 4 cores, and we see how all the tasks are running and fully utilizing the available resources. So to finish this presentation, I want to give some more details about the scheduling. So since we want to target real-time guarantees, we need to provide some advanced scheduling capabilities. So what we do is first we do an offline profiling of the task that we want to execute and the capabilities of the available resources. So we generate the tasks and we execute them a number of times over all the available resources in order to obtain statistics about the task execution times and the data transfer times. So once we do this for all the tasks and all the resources, we obtain the statistics and then we apply the task scheduler. Now, the task scheduler that we have developed for the class project is based on heuristics that aim to minimize the end-to-end response time. So based on these heuristics, this is just an example of how the scheduling would look like. So the different tasks are allocated to the resources based on the time, the estimated time that they need for completion, and making sure that specific deadlines are met. So in this example, we can see the specific deadlines of each task individually and the end-to-end response time. Now, the key advantage of this is that it enables us to have an idea, an estimation of the end-to-end workflow response time. And this enables us to say that if we execute our workflow in this specific architecture and infrastructure, we can guarantee that it will be executed in this time. Now, of course, we cannot guarantee it always because there are unpredictable events. So what happens if, for example, the focus node 2 comes down or becomes congested for a reason? So our workflow is capable of adapting to this change in real time. So if, for example, FOC2 becomes unavailable, then the comms orchestrator will notice the increase of the response time and that the deadlines of the different tasks are missed. And in that case, it will reschedule the tasks, making sure that everything is executed smoothly. So the task will not be assigned to FOC 2 anymore and will be allocated to the remaining available resources. Now, of course, this will lead to the calculation of a new response time, but this is what we can do with the given resources that we have. So concluding, we have seen the capabilities of the class software architecture, and we have seen how it can aid to the development, distribution, and execution of the complex analytic workflows over the complete compute continuum in a way that is transparent to the programmer and agnostic to the infrastructure. And we also saw how we can provide real-time guarantees while supporting the reallocation of resources and the scaling also in real time. So that's all. I'm out of breath.
Thanks very much, Ellie. That was fantastic. Thanks very much for your presentation. And thanks to all the speakers, actually, because this wraps up all the presentations for today, well, apart from the final one from Eduardo. But let's move on. Let me share my screen once again to just check the agenda. So I think now is the perfect moment to have our longer Q&A slot. So if the speakers in the Modena room can gather, and we also have Ruth, of course, from Spain online. So let's use this time for any questions and answers that our attendees have had. I already have a few that I have had collected earlier. So let me stop sharing now and let me also spotlight Ruth. Okay, so perfect. Let me ask the first questions that we had. So the first question says, how have the components communicated between the cloud and the vehicle? The REST API MQTT.
That I guess you can answer.
Okay, so as discussed before, we deployed the lightweight protocol, which is the MASA protocol using UDP. And since we had to communicate from the cloud to the car, we used this kind of strategy. We used a more, let's say, flexible way of doing that using MQTT to be able to communicate from the cloud to one of the fog nodes. And then since the fog node can access the 4G network, it will be using the MASA protocol to send the notification to the car.
Thank you. Thanks, Roberto. Let's move on to the second one. So we have a question that says that although maybe it's not in scope to optimize the latency, have you measured it? For instance, in the live demo that you showed, did you attempt to measure latency, optimize?
Yes, yes. Okay, so yes, we have done this. The latency of the end-to-end workflow, meaning from the time we are gathering the cameras, the images from the cameras, till the time this information is at the cloud level, ready to be consumed by Ethops and by Rotterdam. We are taking in average between 70, 80 milliseconds up to 120 milliseconds. Then in the cloud, and this is, you probably can answer better this question, how much latency we are taking on the cloud level?
So what we did is basically we benchmarked the computation in the cloud under different loads. I can tell you that for subsets of objects that are below 200 objects, we get commonly less than 200 millisecond the computation. But of course, we stressed the system to much higher loads than what we get in just using synthetic data. And there we were able to push it up to, let's say, some reasonable limit of 500 milliseconds, which is something we derived from a stopping distance calculator, given the road conditions and the climate and all that. The perception time, the total perception time needs to be no more than 500 milliseconds, give or take. So this was also the limit that we did for benchmarking the cloud computation. And we saw that we were able to process for collision detection, for example, groups of 1,200 pairs of collisions in such a time for 500 milliseconds.
Yeah. And in the end, from the cloud to the car, for the actual, is less than 20 milliseconds, because there is the communication from MQTT to the fog node, which is instant, mostly less than a millisecond. And then there is the delay of the 4G connection, which is about 16 milliseconds, 16 milliseconds.
So at the end, we are, the project has been, as Erez was commenting before, tried to provide end-to-end. We get the data, the car receives the alert within the range of 500 milliseconds. And considering the speed of vehicles in the city, it's a reasonable time.
Yeah, if you look at the video, for example, the good result that Edu showed, the good result video that Edu showed, it's almost visible there, where you see the notifications appearing between half a second, sometimes more, maybe even a full second before the actual collision could occur.
Mm-hmm. Thank you. Thanks very much. And there is, well, it's an additional question about latency, which I'm pretty sure you've covered already. I'm gonna ask it anyway, and then you confirm. What is the additional latency introduced by the cloud computation?
Yes, I think we have answered. But
yes,
if you want to comment, but I think we have answered.
So as I said, we stressed the computation at various scales using synthetic data to go beyond just the real loads, and the numbers we got for the gross computation. I'm not sure we actually benchmarked the overhead. It's actually detailed in the forthcoming deliverable that is about to be submitted for class. And I'm trying to recall more exact numbers there, but I would say that more often the overhead was around, we sometimes were able to get it to less than 20% of the actual, the total computation.
Mm-hmm. Okay, great. So I move on with the second question. Not second, but the next one that says, again, maybe it's out of scope, but maybe not. The question says, how is the energy efficiency at the edge computing achieved? It was mentioned by Edu at the beginning of his presentation.
Okay, so this is not something that class has been addressed. Mm-hmm. In the sense that we are not dealing with energy efficiency, but what we have done is considering or benchmarking the different analytics on different type of processor architectures, as Roberto shown, and we have tested a number of different devices, starting from the NVIDIA Jetson TX2. That if I recall correctly, the energy is between 10 watts and 30 watts, more or less, depending on the modes. We have been also using Javier Jetson Javier, that is a bit more powerful. It's more in the 20-30 range. And then we are also being tested in more powerful NVIDIA boards based on Volta, which the power is significantly higher.
Just as a comment on in the beginning of the project, while we were choosing the architecture on which to run our analytics, we also benchmarked different kind of platforms, such as FPGAs or standard ARM CPUs. But for the needs of the computation of the analytics, in particular for the inference, we were tied to use NVIDIA GPUs, because otherwise we weren't able to obtain the kind of performances that we were needed to achieve to obtain our real-time requirements.
And here let me emphasize kind of a side comment, not related to energy, but I think it is a good point to emphasize it. So we are running the exact same the exact same workflow on different platforms. So we are running this on the Jetson families. We are running this on more powerful families, more powerful NVIDIA's families. Just to stress the portability. I was I was mentioned at the very beginning. And in fact, there is I've seen a question that perhaps at some point, Nicoletta, you are going to make it. So let me take this opportunity to advance to this question that was about something like if this is portable to other cities. And the answer
yes,
is absolutely yes, because portability is one of our key performance indicators. Okay, so the whole thing can be run wherever we want. We are not tied to NVIDIA's as well, so we can use any other type. The only thing that is that this has been implemented off top of NVIDIA's, as Roberto said, because the performance was very, very nice. But our technology can be ported in any platform. Even we could do it in a small Raspberry Pi. The performance, of course, would be a disaster, but this is perfectly.
It all depends on the analytics.
Exactly. It should be stressed also that we are not tied specifically to V2X applications. Class is about doing real-time processing of big data in the cloud and the edge in general. Okay, so you could do that on a factory floor, just like you do it in a V2X, just like you do it in controlling some fleet of machinery, some sensoric response in other platforms, etc.
Yeah.
So I think you are covering different questions that they came. So, for example, there is one about V2X that says, is the platform ready to work with V2X-C, V2X protocols?
These I'm not familiar with the V2X-C protocol.
Cellular V2X.
We are ready since we are using 4G, and we have also other projects in the MASA area that are working with DSRC or other kind of protocols, in particular for automotive. So we are able to use the same architecture, because the only thing is that the communication media will be a different
However, it should be stressed that one fundamental difference when it comes, for example, to running on top of a 5G MEC is what Edu proposed earlier about not owning the infrastructure, because it's unlikely that in that case, the MEC would be dedicated to class. It's more likely that this MEC will be provided by a third party, by a telecom organization, where the class architecture would be in fact renting or leasing resources from that MEC and using them as the edge devices in effect. And the lack of hardware control poses some interesting challenges, as Edu explained earlier, about providing the same quality of service. But I believe this is a topic that is going to be looked into very deeply in the near future.
And there is another question that you already touched upon, but it says, is the class platform open source and ready for reproduction? What is its maturity and business model?
Okay. So it's open source, but it is not a product. It is a prototype.
It's a prototype.
So the maturity of the components are different. So there are components that are very mature that has been developed. For example, comms, it's quite mature component, has been developed for the last 10 years. BSC OpenWhisk is definitely a mature component. Data Clay is not mature at all. So there we are having some difficulties. I mean, it's just I said is a prototype that can be tested. So the message is it works end to end, but it's a prototype, and as a prototype, there can be failures.
But if you think about the general picture, class bears a message of a software architecture, which means if you organize the components in such a way that these provide specific functionalities and capabilities, and these we can deliver an interesting and useful applications on top of them. So this is actually a broader message than just locking down into each specific. It doesn't have to be OpenWhisk. It doesn't have to be, for orchestration, for combining orchestration, serverless, data propagation, and all these capabilities.
Indeed, this is an excellent comment. So all the proposals we have developed in the project can be extended to other type of platforms.
Right. So this probably answers this additional comment that says that this is a good approach, the neutral host business model, but what about the scalability of it?
Scalability in terms of more resources, scalability in terms of workflow complexity. I mean, there are different types of
There is an answer to that from the person that asked about it, and he says workflow and resources.
Okay, good. Okay, so so here scalability. So in terms of resources, the more resources you have, the more potential communication impact you have. In this case, our analytics, our heuristics to distribute the workflow takes all this into account, but this makes the scheduler more complex. The same thing applies to the workflow description. The bigger it is the workflow, the more difficult it is to find, let's say, a good solution, or the heuristic will be difficult to find a more good. But here I'm really thinking of scaling to a lot of nodes, okay? So just to put you an example, COMS that we are using is being applied to the Mare Nostrum supercomputer. There we are having 5,000 nodes. Okay, so in that respect, but of course there is a very controlled scenario in which communications are through InfiniBand. So it's much less complex, like in the heterogeneous scenarios we are dealing with. But in any case, I think we are prepared. Class is prepared to scale to larger. I don't know if you want to comment something else.
So some components have built-in innate abilities, for scaling out, OpenWhisk. They are already prepared to launch multiple control points, and a very large scale of functions. But the overall, any questions for scale, we can always present a good prediction, but eventually what the real testimony is empirical results. So right now we believe we can scale the current prototype to larger scale. How much is that? Where do we find new bottlenecks? Because we have found bottlenecks in the past and got around this. I think a fair answer would be, we'll have to test and see.
Yeah.
Okay, right. Next question. What about extra power consumption? Have you done an analysis on that?
Energy.
And extra power consumption. Have you done any analysis on that? A great part of the roads has no access to power for these attendant edge nodes.
Okay. So no. So we have not focused on energy at all. So we have not, let's say, we have not made an analysis of the trade-off between what is the extra energy we need in order to have a more powerful machine. So this was not energy is not focus of the project, so we have not addressed this.
Okay, it's not in the scope. And I think I have a final question that it's a very good one to post last, because it's about the future. So it says, what is the plan? What is the plan post-class? What are the open challenges ahead?
Okay. Yes, I was in fact expecting this question. So the challenges are many. So the first one that I already mentioned before and that Eres has already commented is that first one, we are considering full control over the resources, and this is okay for now, but this is not going to be in the near future. Is not going to be the case because the cloud model is going to be extended, or I think that the cloud model is going to be extended to the edge as well. So there are going to be much more difficulties in order to control. Then there is always the 5G, right? Whenever we are 5G enters in the game, and then you also can control the way communications are done. It's also a challenge. Then there is the cloud wall. It's evolving constantly with new open source projects that with new techniques that really need to stay in tune. For example, the serverless model
is constantly evolving.
Yes, it's constantly evolving. So far, we have applied this to the cloud level, but the next step is what about to apply this to the edge level to provide another extra layer of abstraction.
It's not just consider general issue, for example, of non-functional requirements in applications in general. I mean, think about it when you deploy your code. Obviously, you have your functional requirements, which means I need to accomplish this task A, task B, task C. I need to do this stuff. This is what my application needs to do. Okay, but then there is the non-functional requirements, because you need certain degree of reliability, you need certain latency, you need certain control of locality, interaction with other components, so-called composability, many other features that are actually very, very hot requirements for modern applications, because when you deploy for enterprise, for example, you got numerous requirements of reliability, of sustainability, of durability of data, et cetera, et cetera. And doing and trying to provide a real general purpose solution to all these non-functional requirements is becoming an extremely arduous chore. Yeah. So this trying to design forward is, I would say, honestly, I mean, I would say, let's just taking a subset of these non-functional requirements and doing in this ever-changing world where you get less and less control is going to be an extremely interesting research challenge for the forthcoming.
There is food for a lot of research. And now, for example, the automotive industry is starting, to shift their attention to cloud and to edge. And then, as Eres was saying, you need to port all the requirements. So how you can execute a safety critical system in an edge cloud environment. In the class, we have tried to provide some light, okay, in this huge, enormous challenging by investigating on the real time. But there are many other requirements. Security is another huge requirement.
Energy that
you just mentioned. Safety in the general term, that there is resiliency, robustness, reproducibility. I mean, there is a lot of research topics that we really hope that we can continue pushing.
Mm-hmm. Thank you. Thanks very much. I think that question was perfect to wrap up this Q&A slot. So we already answered quite a lot. Thanks everyone for asking questions. It was a very interesting part of the event, I think. And let me share my screen again, just a final time to share the agenda so that Edu can have some time to prepare for his very final conclusion. It's going to be a very short conclusion about the event and about the project. And I have already shared some links in the chat for everyone to see. I have shared our website, also the class GitHub channel where you can find the software components there. I have also shared links to our social media, so it would be great if you follow us on there and stay tuned with the things that we're going to do from now on. Of course, the project is finishing, but we're still planning to get out more material. So stay tuned, and also don't forget that the recording of this event will be posted online, and you can just catch it up whenever you have the time. So Edu, if you're ready,
I'm ready.
Great. So we can just have your final presentation. There
Okay,
you go.
so this is going to be very, very fast. So let me summarize. So here, I would like you to have two take-home messages. So the first one is about the software architecture, okay, in which the objective of the software architecture is focusing on try to enhance the development, deployment, and execution of complex workflows across what we call the compute continuum, taking into account real-time requirements, and really focus on the productivity. Okay, so enhancing the productivity to facilitate this design and execution of the complex workflows, and also and the second message is the use of this software architecture in order to implement these two use cases based for the collision detection to potentially be included in future advanced driving assistance systems, and the capability of monitoring in real time what is the level of pollution of a given area based on the actual mobility of the different vehicles. That is where it is the benefit. Just let me show you the last technical slide. This slide, I mean, this is the demo this is the demo that you have seen, in which the two Maserati cars were approaching, and the city plus the information from the car were fused in order to detect the collision. And this is precisely what we have been showing you during the different presentations, how we are describing the workflow using both combs and lithops, how we are deploying this, okay, using our scheduling mechanisms, and how the different technologies that we have been presenting they interacts among them in order to make this execution possible. And my last slide is just to say thank you very much for the whole consortium, and especially for the last part of the year, because this use case has been very challenging, but has been very challenged to do it with all the team locked down without the cars. Okay, so our original plan was to start the test in April 2020, but you know what happened in April 2020. And in fact, we had access to to everything again with the whole team in May 2021. And so with 1 year, the team has done an extraordinary work in order to try to test a use case without having the cars, which has been quite challenging. But considering these difficulties, I think all the team has done a great job. So the only thing I can do is to say thank you to the consortium. And that's all from my side. Now we have, so thank you very much for attending.
Thank you.
This event has been a real pleasure to be here as well. And now, Nicoletta, I think we have prepared a short video.
Yes. I think it's time to show this video just to conclude this event and the project. I would suggest that all the attendees stay tuned. It's a 2-minute video that we made in Modena with all the cars and the use cases. So it would be great if people stayed to watch it. And yeah, I would also like to thank everyone, the speakers that were great today presenting, all the attendees that came to our event today. It was a pleasure to have you and to answer all your questions. And stay tuned, that's from my side.
Imagine a city where data is shared between the city and cars in real time to implement smart mobility functionalities for traffic management and advanced driver assistance systems. This is exactly what the CLASS project is doing in Modena, Italy.
The extraction of knowledge from data coming from sensors located in the city and in vehicles requires to effectively combine edge and cloud computing paradigm into single computing infrastructure. To do so, CLASS has developed a new generation software architecture for the development and execution of advanced big data methods that will enhance the interaction between vehicles and citizens in urban areas in real time.
The CLASS software architecture integrates technologies from various computing domains, including IoT, edge and cloud computing, that combined with mobile communications, enable the extraction of knowledge in a fully distributed ecosystem that spans across the compute continuum. The architecture has been evaluated in the Modena Automotive Smart Area, MASA, a real-life urban laboratory equipped with sensors and advanced connectivity, in which 2 high-tech equipped Maserati cars provide continuous monitoring across 5 defined scenarios. The CLASS technology allows the data collected by MASA and the 2 vehicles to be efficiently processed and combined to increase the sensing capabilities of vehicles and cities, therefore helping to anticipate hazardous situations, creating a safer mobility scenario for future smart cities.
Grazie al progetto CLASS abbiamo potuto testare le più innovative tecnologie per lo sviluppo della Smart City, aprendo la strada per innovazione nell'ambito della mobilità urbana e migliorando la qualità di vita dei cittadini.
CLASS has combined the proud Italian tradition of high-end cars with the needs of modern smart cities, enhancing the capabilities of connected vehicles.
We really hope that CLASS will contribute to the way smart cities are evolving in the near future.